Everyone. Come to IMSE881 Linear Programming Lecture 9. This lecture we're going to talk about Dantzig-Wolfe Decomposition. It's a decomposition technique using for solve a problem with special structures, and especially with a large size. And the contents of this lecture is also from the handwritten handout, page 75 to 82. Okay. The Dantzig-Wolfe decomposition algorithm was developed in 1960, actually a few years after the simplex method was developed, okay, and proposed. And is initiated by extensive work on the large-scale mathematical programming, especially linear programming, which has followed many other variation of algorithm. And this type of decomposition algorithm and has typically nowadays has two different types. The first type is a so-called column generation algorithm, which is based off the Dantzig-Wolfe decomposition algorithm. The other type of algorithm is called Benders decomposition. Basically, it's decompose the rows of your constraint matrix. Here, what we have is basically it's also decompose the rows and set of constraint you have, and but we're using a column generation scheme to generate new column each iteration. Okay, and Benders decomposition method is generating the row each iteration. And so there are two different types of popular decomposition technique to solve a large-scale problem. And let's focus on this lecture, the column generation or the Dantzig-Wolfe decomposition algorithm. And the problem structure looks like that. Initially, you have a set of constraint A, which have a fairly special structure. And for example, the A1 matrix you have all together. The B1 matrix is a so-called block diagonal structure, which means only a few of the decision variable actually involved in those constraints. So we have a so-called B1 is a block, and B2 is another block involving second set of a variable, and B3 is another block of a variable which is involved. But A constraint involves the entire variables and involve all that. So these type of large-scale problem with a special structure, and you can see that for the B matrices, and the off-diagonal elements are majority 0. So there's really, can we explore the special structure we have right here in order to solve these larger scale problems. But before we solve that, let's introduce a couple definition and couple theorem. And most of those we already talked about before. And let's focus on the first one. The first one is S belongs to R of n and Euclidean space over n, and it's a convex if and only if all the x's, okay, if x1 and x2 belong to the set S, then any convex combination of x1 and x2 also belongs to the S. Okay, this is a so-called convex combination. For example, the polyhedral theory, and ax less than equals to b, and the x is non-negative. This type of constraint feasible region is a convex set. Also, if x1 to xp belongs to the n-dimensional Euclidean space, this set of H convex Hall constructed by x1 to xp is basically the convex combination for x1 to xp, and we call this convex Hall. And the convex Hall definition is fairly important. Later on, we could use it for even non-convex feasible region, or many times the integer programming type of a situation. We have to using a convex Hall in order to maintain the feasible region as convex instead of like a zigzag or discrete in the integer programming session. Okay, we'll talk about the next. The theorem 1 here states, if a S is a set of point x, okay, so those x satisfying ax equals to b and x is non-negative, it's a non-empty and bounded. If it's a bounded, and let x1 to xk are the extreme point of S, then any x belong to S may be represented as a convex combination of all the extreme points. And this, we proved this in the polyhedral theory earlier in lecture 2. Okay, theorem 2, basically if the feasible region S, x equal to b, and x is non-negative, so it's non-empty but not necessarily bounded, then any points inside S can be represented as a convex combination of the extreme point of X and the cone combination of the extreme direction, D1s to dp. Okay, so these are the general results from the polyhedral theory in lecture 2. And we just remind you again, and we're going to heavily use this concept to define our decomposition problems. Okay. Consider the following linear programming problem, and the standard form still is C transpose minimize as C transpose times X, and based on subject to xa times X equal to B, and X is non-negative. However, the constraint A right here has a very special structure, okay? And I have a so-called a set of constraint A1 to AP, and represent P segments of a first part of this matrix, and we call it A1 hat. A1 hat has M1 rows and columns, and for the rest of them, okay, B1, B2, represented by B1, B2 to BP, are we'll call the A2 hat, which have M2 times N columns. So I have a N decision variable, but usually we referring this first part of the constraint A1 is a so-called difficult constraint, and the second part of this constraint we call the easy constraint. Why they are easy? If we can ignore the difficult constraint, actually there's a huge problem. We can dissect them into what? P-independence problem, P-independent linear programming problem to solve it. So if we can, in some way, to ignore this difficult constraint in the beginning, and then we can solve these smaller size of a problem involve B1, B2, B3, B4, and only involve several of the decision variable each time. So we can solve them separately, and then we can combine the optimal solution for these P different problem and make it an optimal solution. If these optimal solution are for each one of those subproblems and satisfying the difficult constraint. So we need to develop a scheme, actually, temporary relief, okay, or forget the difficult constraint and trying to solve the problem individually using a smaller size and even parallel processing nowadays. And then we put together the solution from each one of the subproblems, and we're trying to fit into the global constraint, the difficult constraint. And many times in the literature, you will probably see that, and these A1 matrices represent the constraint called the global constraint. And the A2 involving all the B matrices are so-called local constraints, okay? So, for example, you have a capital budgeting problem, and the headquarters is trying to determine which project belongs to each one of the branch office. They have a different type of constraint. So the B1, B2, B3, B to the BP represent each one of the branch office. They have their local constraint. However, A1 to AP represent the constraint involving the global across the company, all the divisions. So, and we have to find the optimal solution for each one of the branch office, and trying to see the optimal solution fits the global goal of the headquarters or the entire enterprise. So we need to develop a special type of algorithm dealing with difficult constraint and the easy constraint back and forth. Okay, we're going to using the polyhedral theory we talked about before. If S2 is bounded, okay, then S is bounded, then x1 to xk will be the extreme point of S2. Then any points in S, okay, can be represented as a convex combination of x1 to xk, so k of those. We can rewrite our original problem using a so-called respect to all the extreme point in their feasible region. And when the lambda will be the weight for each one of the extreme point. So basically the constraint is plug in the convex combination of all the xj, all the extreme point. Of course, since it's a convex combination, the total of the lambda, the weight, should be equals to 1. So we can further represent our model in this way. Okay, and actually the C transpose times xj times lambda j is right here. And also constraint we can using A1 hat times xj times lambda j as well. Okay, here we're only dealing with the difficult constraint right here. And of course the lambda is non-negative, and the summation of the lambda, the sum of the lambda equals to 1. Here we can do a very simple so-called variable substitution. We substitute the C transpose times xj, we call the fj, okay? And the A1 hat times xj, and we're using another symbol called pj. So this we can simplify the models a little bit, because each one of the xj is supposed to be a fixed point, and they're not decision variable, and we just have to find out how many extreme point I need, or minimum number of extreme point I need to define the optimal solution. Since instead of finding the optimal solution, I just need to find how many extreme point I need to find the optimal solution. So that's why we're doing this so-called variable substitution. C transpose times xj, we call it fj, and the A1 hat times xj, we're using a pj. So next slide show you the result. And this problem only involved the difficult constraint, and we refer this as a master problem. And the master problem equals to the minimization of summation of fj times lambda j. So all I have to do is determine my decision variable in the master problem are the lambda. Okay? Since we already know the fj's are extreme point, they're fixed point, we just have to figure out the weight of the convex combination. Similar situation happens to the constraint. The pj equals to A1 hat times xj as well. So the only decision variable in the master problem is the lambda as well. All right. Of course, sum of the lambda equals to 1. Lambda is non-negative. This is pretty straightforward. What I'm trying to do is omega, and the corresponding do variable for the master problem, omega. Omega is corresponding to the original A1 constraint, and we call it omega 1. And it has a dimension of m1 times 1, okay? m1 times 1, so I have a vector of omega 1. Depends on how many constraints we have in the A1, which is the difficult constraint. And also we have one single do variable, omega naught, is the do variable respect to the convex combination constraint, okay? Convex weight constraint. And also, rather than tabulating all the column, we're going to be using a so-called column generation technique to create a column enter to the basis every time. Remember, for solving linear programming problem using simplex method, what we do is we try to find the value of zj minus cj for the non-basic variable, and then whatever zj minus cj is the largest, and we choose that as an interim variable. So basically what we do is we don't keep all the non-basic variable in our tableau. We're just trying to find a column which is a non-basic variable and see if they can enter in our basis for the master problem. And look at the zj minus cj is basically equals to omega transpose times pj, and pj is the a1 hat times xj, and 1 is corresponding to the omega naught, okay, minus fj. Fj is what? C transpose times xj as well. So basically it's you have a vector of omega 1 and you have one single omega naught, okay? And so becoming omega j, okay, omega 1j times pj and plus omega naught times 1. So this is actually it's your do constraint in your master problem. So that's fairly easy. We can calculate, if we can, calculate for each one of the j. J means what? Each one of the extreme point. If all the zj minus cj for all the extreme point, okay, and it's less than or equal to 0, then we know I already have the optimal on hand, okay? If otherwise we find sum of the zj minus cj is greater than 0, then we can solve a very simple problem and try to maximize, okay, the zj minus cj. So, but zj minus cj now can be rewritten as this format, okay? Omega 1 transpose times pj and plus omega naught minus fj. So pj, of course, equals to a1 hat times xj, and fj equals to c transpose times xj. So xj's are the extreme point. But we don't know the extreme point at this point. We're assuming we know. And where will we find this extreme point for the, the region? And what we have is basically we can convert it back into the maximize of omega 1 transpose times a1 hat minus c transpose times xj plus omega naught. Okay, so we can break it back to the original format. And then we're going to use this as my objective function to solve the following subproblem. So the subproblem's decision variable is still x, and we're trying to using this as objective function value parameter. So omega 1 transpose times x1 hat minus c transpose is my cost coefficient for the x. Then the omega naught is just a constant in that case. And of course, for the subproblem, I'm going to focus on the easier constraint, called A2 hat times x equal to B2, and x still is non-negative. So every time we solve the subproblem, we find out the maxima of those zj minus cj, and we pick one of the extreme point as the one to entering the basis. Okay, so still we're following exactly what we did. We're just using another linear, smaller linear, another linear program and trying to find the entering column, since the problem may be fairly large in size, have involved all the global constraints. But the nice things about solving this subproblem is, like we said it before, the subproblem for this part, okay, it can be separable, can be separated into p separate problem, okay? So if the subproblems as objective function is less than or equal to 0, then we have to stop, okay? So the best we can find, the extreme point, the zj minus cj, is less than or equal to 0, and everything else is even more negative. So we know we already have the optimal hand. There's no way to improve my global optimal objective function. If we can find one, it is positive, then look at this problem we have, okay? The problem we have right here, even the, we have the current omega 1, we have input data A1 hat, and we have the input data cost coefficient C transpose, and we have the current omega naught as a due solution. But look at the A2 matrix, they are block diagonal information. So we can separate each one of these subproblems into p smaller size problem and solve them independently. Then we combine them together as a whole.